Welcome to the Crazy Hat Chemist. So another video here on acids, bases, and titrations. Wait, before I do that, I'm going to make sure that you have reviewed, okay, acid-base titration video 21 part A, because this is part C. Hopefully you've done part A and part B. This is part C. All right, here we go. Bam! So today we're doing titration example number 3. Okay, we're doing the equivalence point calculation, the most complicated mathematical problem here on any of the titration points. Okay, we're going to calculate the moles of acid, okay, which is the moles of acetic acid. So we have the volume and we also have the molarity. So we have the volume of 50 mils. We're going to use a unit conversion to convert from milliliters to liters. And then the next unit conversion is using the molarity, which is moles per liter. And that's 0.1 moles per 1 liter. So I got 50 mils divided by the 1,000 milliliters to convert to liters, and then multiply by 0.1 moles per 1 liter. That gives me 0.00500 moles of acetic acid. Now, that's how much acetic acid I have inside the flask or the reaction vessel initially before anything happens. That's as much acetic acid as I have. Now, at the equivalence point, the important point here is what's driving all this is that the moles of the acid are equal to the moles of the base. That is the definition of the equivalence point or the end point of the titration. The moles of the acid are equal to the moles of the base. Okay, so knowing that, we know the moles of the acid, and therefore we know the moles of the base that are necessary at the equivalence point. So the moles of the base is 0.00500 moles of sodium hydroxide. Knowing that moles of sodium hydroxide, now we're going to calculate the volume of sodium hydroxide that's necessary at the equivalence point. So we're going to use this mole value and the molarity. So we've got our moles of sodium hydroxide at 0.00500 moles. We're starting off with that. Then we're using the molarity of the sodium hydroxide. Remember, we took the reciprocal of this so that we keep the moles in the denominator, the volume in the numerator, so that the moles cancel out. Then we're going to convert this from liters to milliliters by multiplying by 1,000. And then we get this value of 50.0 milliliters of sodium hydroxide that is necessary at the equivalence point. And I don't know if you remember this, but in part A of this video, of this example number 3, of titration example number 3, I pointed out to you that there is something very important about this. And because the molarities are the same of the acid and the base, then something special is going to happen. And that something special is right there. That 50 milliliters of base that's required is the same volume of acid that you have. So, without doing this calculation, you could have understood that conceptually, and now you actually know how to do it mathematically, but hopefully you understand it conceptually. Since the molarities of the acid and the base are the same, the volumes will be the same at the equivalence point only. So now we're going to calculate the total volume, and this should be a very easy, simple calculation for you. You got the milliliters of the acid and the milliliters of the base. That's 50 milliliters for both of them. You're going to sum those up, and you're going to get 100.0 milliliters total volume. Okay, now from here, we're going to calculate the concentration of the conjugate to the acid. That is the acetate ion concentration. Okay, the acid reacts with the base, and the acid is completely converted into its conjugate base, that is acetate ion, and that will be in a new volume, and this will be at the equivalence point. So we're calculating the concentration of the acetate ion at the equivalence point in this new volume. The moles of the acetate ion is the same as the moles of the acetic acid, because all the acetic acid has been converted into its conjugate. So I've got 0.00500 moles of the acetate ion at the equivalence point. And this is in a total volume of 100 milliliters, and I've converted that into liters there for you by dividing by 1,000. Now, I'm going to take those two numbers right there, the moles and the liters, divide them, and I'm going to get my value for the molarity, that is the concentration at the equivalence point of the acetate ion. And that is 0.0500 molar. Okay, got that so far, hopefully. Okay, at the equivalence point, all of the acid has been converted into its conjugate, the acetate ion. Therefore, a new equation must be written, and then the appropriate K must be written, which is a switch of the K. Okay, starting with the conjugate to the acid for the next ice table setup. Okay, that's going to be on this next slide. Okay, so we've got the acetate ion, okay, plus water. Now I'm going to write the conjugate pairs to both of these. Okay, now the acetate ion is not an acid, it is a base. Therefore, the conjugate to water is going to be a base, and that is hydroxide ion. You should also see that the conjugate to the acetate ion is acetic acid. You should also see that both the reactant side and the product side both have a net charge of -1. Okay, that's another way to actually determine what the product is. If you look at just the reactants with the acetate ion and water, you should see that the acetate ion is a -1. Okay, and hydroxide is a -1. Therefore, that is the ion that's going to be on the product side, since the water is neutral. And the water is going to donate that hydrogen to the acetate ion to give acetic acid on the product side, and that's that neutral compound there. Hopefully that makes sense. Concentration, okay, the conjugate pairs. Okay, we're going to do an ice table. That's initial, change, and equilibrium. We just calculated, we spent a whole bunch of time using the moles of acid equal the moles of base and then the total volume to calculate the concentration of the conjugate to acetic acid, which is the acetate ion, which is this number here, which is 0.0500 molar. Okay, how much water do we have? Nothing. Okay, how much do we have on the product side? Like any equilibrium problem, 0 and 0 for the products. Okay, now in the change column, okay, this will shift like all equilibrium problems from the reactants to the products. That means the reactants will decrease, the products will increase. I have stoichiometric coefficients of 1s across the board here. So it's a -1x and nothing for the water because it's a liquid, and a +1x and a +1x for both of the products. I'm going to add up the I and the C, that's the initial and the change, to get my equilibrium, and I got 0.0500 minus x, nothing for the water, and an x for the acetic acid, and an x for the hydroxide. Now, I'm going to write the Kb expression. I have to write a Kb for the base dissociation constant because I have a hydroxide ion on the product side and not the other, which is the hydronium ion. Okay, so it's going to be a Kb because it's a base. So products over reactants, stoichiometric coefficients as exponents. I got a Kb is the acetic acid times hydroxide divided by the acetate ion. Okay, now I need to solve for the Kb. So in order to solve for the Kb, and I was given the Ka, I got my Kw is equal to the Ka times Kb. I'm going to plug right into this here. So 1.0 times 10 to the -14 for the Kw. 1.8 times 10 to -5 for the Ka. Divide both sides by the Ka and I have my Kb. My Kb is equal to 5.6 times 10 to the -10. That value is going to go right into here for the Kb. Then I'm going to plug in my equilibrium values right in there into that Kb expression, and then this is what I'm going to get. So I have 5.6 times 10 to the -10 is equal to x squared divided by 0.0500 minus x. Now, I'm going to always ask this same question. I keep on repeating myself on this one, but hopefully this works here. 100 times a K, is that less than the initial concentration? If so, I do not have to use the quadratic. So 5.6 times 10 to the -10, that's my K. 100 times that, is that less than 0.0500? Yes, that is the case. So if that is the case, I'm going to get rid of that minus x in the denominator term, and now I do not have to use the quadratic. I can use the approximation. So mathematically, you're going to plug this into your calculator like the following. That is 5.6 times 10 to the -10 times 0.0500. Take the square root of that, and bam, that's the number you're going to get. X is equal to 5.3 times 10 to the -6. Now I'm going to go look at my equilibrium ice table. What does X equal? X equals the acetic acid concentration at the equivalence point. It also equals the hydroxide ion concentration at the equivalence point. So what does the hydroxide ion concentration equal? 5.3 times 10 to the negative 6 molar. I need to solve for the pH. That's my ultimate goal. And there are a variety of different ways. I could use the POH, or I can solve using the KW. Either way, I'm going to use the POH here, which is the negative log of the hydroxide ion concentration. I get a POH of 5.28. Okay, notice it has 2 decimal places. I still need to solve for the pH. The pH is going to be pH plus the POH is equal to 14.00. I'm going to plug in the POH into this and then solve for the pH by subtracting 5.28 from both sides. And I'm going to get a pH of 8.72. Okay, 8.72 is the equivalence point pH. Okay, hopefully that value makes sense. It should, because I am titrating an acid with a strong base, and at the equivalence point, the strong thing always wins. Okay, and that's why that pH is greater than 7. So it is basic, as you would certainly predict. And again, just to reiterate, okay, when is the pH 7 at the equivalence point? When you have a strong acid and a strong base, or a strong base and a strong acid. Either one of those. Okay, I'm not done yet. I still got more. Okay, here's a little bit of titration humor to interrupt this a little bit. Okay, what did the weak acid say to the strong base? Let's meet at the end point. Okay. What did the weak acid say to the strong base? Feels like I'm repeating myself. You're so strong, you make me feel weak. Okay. Roses are red. Thymophaline is blue. There is no endpoint for the love that I have for you. That's why I want you, of course, to go to my website, thecrazyhatchemist.com, donate, okay, because it takes a tremendous amount of time to make these videos, and I will send you a sticker or maybe even a t-shirt. Super cool. Little intermediate advertisement there. Okay, let's keep on going. Okay, what is the best indicator to use for this titration? So, since the pH is equals 8.72 at the equivalence point or the end point of this titration, one should choose an indicator which changes color at or around this pH. Or if you know the pKa of the indicator would be equivalent to the pH at the equivalence point. Okay, and upon analyzing that chart that I had on a previous video, phenolphthalein would be the best indicator as it changes from colorless to fuchsia or pink at or above pH 8. So that would be the best one since this pH is 8.72 at the equivalence point. Okay, I am the Crazy Hat Chemist, and of course I can't end here without a crazy hat. So, give me a thumbs up if you like that video. Subscribe to my YouTube channel. Find me online. Please donate to my website. Love you. Talk to you later. Bye now.